Let's wrap up section 7. So this is the bottom of page 18 in the note packet. And we left off most of the, well, partway through this. Actually, it continues on the top of the next page, but just to kind of get back into the flow of things, here's what's going on. It's talking about the relationship between torque and angular acceleration, something that would be the rotational counterpart to F equals ma. And that torque equals a quantity called the moment of inertia times the angular acceleration This is one of those relationships where you have to use radians. For a point-like particle, in other words, something whose size is very small compared to the radius of the circle that it's going around in, the moment of inertia is mr squared. Now, quite often you're not dealing, I mean, sometimes you're dealing with point-like particles, but more often you're dealing with some sort of an extended rigid body, a lawnmower blade or whatever. And what you need to do then, in order to generalize this, is you have to think of it as being a whole bunch of point-like particles that are stuck together. And all of this applies to each of those particles. So just as an example, if you have a disk like a bench, the grinding stone on a bench grinder, for example, you're going to sharpen the lawnmower blade. So you turn on the motor, and this stone wheel on the end of it starts going around faster and faster and faster. The motor exerts a torque on the system, and it picks up speed at a rate equal to alpha. And the inertia tells you how much acceleration you get from a given amount of torque. Just like in linear motion, the mass, you know, if you compare to F equals ma, when you're talking about translational motion, the mass tells you how much acceleration you get from a given amount of force. Here, the moment of inertia tells you how much angular acceleration you get from a given amount of torque, okay? It's measuring the object's inertia, its tendency to keep doing what it's already doing, its resistance to acceleration. Unlike the translational case, the moment of inertia depends not only on how much mass is there, but also on how that mass is distributed. So, for example, a rotating disc, the brake rotor in a car, or the wheel on a bench grinder, or whatever. There's the center. We're assuming this disc is rotating around its center. Let's say the radius is capital R, and the total mass of the entire disc is capital M. As I started to say a minute ago, what you have to do is think of the disk as being a lot of little pieces that are all stuck together, such as there's that little piece right there, whose mass is a lowercase m, and which is a distance little r from the center. And that's the previous case. Like when I was talking about a point particle going around in a circle, that's what this is. What you have to do is think of the disk as a whole bunch of those stuck together. The inertia of each one is mr squared. To get the inertia, the rotational inertia of the entire disk, you have to add up all of those mr squareds. Now, actually, this is just an approximation, as long as all of these little pieces, and I've only drawn one here, but imagine the whole thing divided into little pieces like that. But, you know, even if they're like 1/10 of a millimeter across, they're not truly point-like. All of this was derived assuming the mass is located at a single point. So it's an approximation to say this. The approximation becomes better if you use a larger number of smaller particles. So instead of a bunch of little pieces that are 1/10 of a millimeter across, have them 1/100th of a millimeter across and have a lot more of them. That's a better approximation, but it's still an approximation. The approximation becomes exact if you take the limit of infinitely many, infinitely small particles. You let the size of each little piece, maybe I'll draw a few more of them on here, it would look better that way. And so on. But you let the size of them approach zero, you let the number of them approach infinity, and then the approximation becomes exact. And so the moment of inertia of this disk is approximately mr squared. Actually, for it to be exact, you have to integrate. dm is the mass of any of the little pieces. So mass times radius squared. An integral is a glorified summation. It's the process I was just describing, where you take the limit of infinitely, it's a summation of infinitely many infinitesimals that are continuously distributed. That's, anyhow, those of you who have completed Calc 1 hopefully know what I'm talking about. Those who haven't, well, this will create a little background for when you get to it in Calc class, a little bit of relevance. Anyhow, when you perform this summation in the case of a disk, it comes out 1/2 the total mass times the outside radius squared. Just as a comparison, if this was a hoop, or call it a ring if you'd rather, all of the mass would be at the outside edge then, okay? In the case of a disk, most of the pieces are closer to the center. So when you add everything up, you get a smaller total. In the case of a hoop, they're all at the outside edge. So this R is equal to capital R for every term in the summation, and you get this. So the same amount of mass distributed differently gives you different amounts of inertia. And this summation, this integral, has been performed before any of us were born for a number of different ways of distributing mass, and the results for, well, anyhow, you can look at your own formulation. Okay, that's coming into focus. Page 3, hoop, a solid cylinder, a solid sphere, a thin spherical shell. They've each got their own formula for each of the different ways you could distribute mass. I don't know how many of you have ever carried a really long ladder, you know, like you're painting the house and you finished this wall, you finished the south wall, and now you want to start painting the east wall of the house. So you take down the ladder and you know, it's like an 18-foot aluminum ladder or something like that. And you're walking along and you get to the corner of the house and you want to walk around the corner and go a little further and then put the ladder up to paint that side. If you've ever done this, maybe you've noticed that when you walk around the corner and try to turn the ladder, it's kind of hard to make it start turning. And once you get it going, it's kind of hard to stop it again, compared to, let's say, a suitcase full of bricks that weighs the same thing. The difference is that most of the mass of the ladder is farther away from the axis of rotation compared to having a suitcase full of bricks that weighs the same thing, okay? So, you know, the bigger R for the little pieces of the object, the more rotational inertia. The reason is to get the object up to a certain angular velocity. I mean, you're not going to get a ladder going around too fast, so let's pick something small like 1 revolution per minute, okay? To get a suitcase full of bricks rotating at 1 revolution per minute, the outside edge of that suitcase isn't really going very fast. Fast in terms of the linear velocity, meters per second. To get the ladder up to that same 1 revolution per minute, the ends of the ladder are going a lot faster because they have to get around a bigger, quite a bit, you know, much larger circle in the same time. So getting most of the mass up to that greater speed requires greater effort. Making it stop again requires greater effort. And so the rotational inertia depends not only on how much mass is there, but on how that mass is distributed. When the mass is farther out away from the axis, you get more inertia. The ladder in the suitcase would take the same amount of effort to slide across the floor, assuming they both had the same friction coefficient. But it's harder to make the ladder rotate because of how the mass is distributed. Okay, so that's the ideas behind all of this. It's time to run through some sample problems. So this first one, here at the bottom of that page, rather than having a continuously distributed mass, you've got, well, a somewhat contrived looking system of 2 small masses on the end of a large lightweight rod that's pivoted at this point right here. Actually, there are some systems that behave like this. If you have, for example, a carbon monoxide molecule, the diameter of the nuclei is about 100,000 times smaller than the distance between them. And the chemical bond, you know, it's the electron cloud that holds it together. The electrons don't weigh anything to speak of. The mass of an electron is like 1/2000th the mass of a proton. So there are actually some systems that would be a lot like this, but let's make up something where we have nice convenient numbers like 2 kilograms instead of something times 10 to the negative 27th kilograms. So anyhow, there's some sort of a shaft here, I guess, which you can't see because of my hand. Maybe if I hold it that way. Okay, so the axis of rotation goes right through there. Somebody's twisting on that, creating a torque of 60 Newton meters. Find the angular acceleration. Well, this is going to be solving for alpha out of tau equals I times alpha. And most of the work will be finding the moment of inertia. Okay. Question tells us that. The question asks for that. So basically I need to figure out that. And once I've got I, the answer drops into my lap. So since we've got just two discrete masses, we don't have to do a continuous sum of infinitesimals like this, like you would for, you know, a rigid body. Rather, you have something which is within the mathematical level of this course, and you can actually just do a, you know, regular addition. So the summation from I, if you're not familiar with the notation here, I is the index of the summation, okay? Little I, capital I for inertia, little I for index. In other words, the subscripts would be 1 for the first particle, the subscripts would be 2 for the second particle, and so on and so on. And this over here is saying that the summation runs from I equals 1 to I equals 2. So for the first particle, you've got a mass of 2 kilograms. It's 3 meters from the axis. And then for the other one, you've got 3 kilograms, and it's 2 meters from the axis. So first term is 18, second term is 12. You add them together, you've got 30. The unit on it would be kilograms times meters squared. A combination of units that has no name of its own. It's just kilograms times squared meter. Units of mass times radius squared. So now knowing that, if torque is equal to inertia times angular acceleration, it follows from that alpha equals the torque divided by the moment of inertia. 60 Newton meters, 30 of those things. As far as the units, well, you know, you could go to the trouble of breaking everything down into fundamental units and canceling stuff out. And actually doing that every now and then is a good exercise. Or the shorter way of doing it is just to remember that it's built into this formula that alpha is in radians per second squared. And with that, we turn the page on the handout. Yes, please. Pardon me for a minute while I play with the camera. Okay, if it focuses on that, and then I slowly sneak it back to where the other page is, I can get it to focus on that. Yeah, there we go. So A lot of what's at the top of the next page here is stuff I've already said. Number 10 there is more of a conceptual question. It doesn't have any numbers in it. So we've got two wheels. They have the same mass, they have the same radius, they both start from rest, they have the same torque acting on them for the same time, same. Everything is the same, except that this one is a solid disc, like a slab cut out of a telephone pole or something like that. This one is a thin hoop, something kind of like a bicycle wheel, where practically all of the mass is located at the outside edge. Compare the final angular speed. So I always kind of pause for a second and ask people to try and decide for themselves, get a little skin in the game. Once in a while, I can coax somebody into saying what they think the answer is. That's obviously not going to happen today because I'm standing here talking to an empty room like some kind of lunatic. But here's your moment to decide. The answer is the disk ends up going faster. And I'll write down a few words about why. As in the one that I just went through. The rate that it picks up speed is equal to the torque divided by the inertia. Okay, since the torque acts for the same time on both of them, the one that experiences a larger angular acceleration will end up going faster after the same amount of time. So the torque on both wheels is the same. That's part of our given information. So if the torque is the same, that means we have an inverse, come on, focus. Thank you. We have an inverse proportion between the angular acceleration and the inertia. So the one with the smaller inertia will be the one with the bigger angular acceleration. Well, you can refer to the formula sheet, and the disk that's the answer. The disk is 1/2 mr squared, whereas, like I said over here at the other end of the blackboard, the hoop is 1 times mr squared. But actually, if you understand, the underlying idea, it shouldn't be necessary to refer to any exact formulas like that. You've got the same amount of mass, but in the case of the hoop, all of that mass is at the outside edge. In the case of the disk, most of it is closer to the center. So you should have some conceptual, if you don't now, try and acquire it. You should have some conceptual understanding for the idea that the rotational inertia is less when the mass is closer in and more when it's farther out. And the disk is, most of the mass is farther in. So you should be able to see that it's the one with the smaller inertia, even without looking up an exact formula. But it happens that you can look up an exact formula if you need to do it that way. Next, number 11. You've got something kind of, sort of, like when you pull the rope on a lawnmower to start it, you know, your rope unwinds and the thing goes around. Only in the case of a lawnmower, there's a lot of resistance in the engine, and so you pull it at a pretty steady speed. Here, we're assuming that this disc is mounted on some sort of frictionless pivot. So as the rope that you're pulling unwinds, this will go around faster and faster and faster and faster. After it's gone around 10 times, probably, you know, that's when you run out of rope. After it's gone around 10 times, how fast is it spinning? Find the angular velocity. It's going to be a two-step process here. I'm going to get omega final from one of those equations that was a couple pages back. Omega final squared equals omega initial squared plus 2 alpha theta. That's what's actually going to give me the answer. But before that'll give me the answer, I have to know the angular acceleration. So step 1, get alpha from tau equals I times alpha. Once you know alpha, step 2, use that other equation to get the answer. So that's the plan of attack. Details will go right here. So step 1 is to get alpha. For I, it's a disk. Says so on the picture. So you go into your formula sheet, where I waved it in front of the camera before. Solid cylinder or disk rotating about center. 1/2 mr squared. Fill in the numbers. Mass, 5 kilos. 0.20 of a meter for the radius to the outside edge. So I've got that number to fill in for I. As for the torque, be careful. People love to get torque and force mixed up with each other. It's worst when you call the force the string tension, because tension and torque both start with the letter T, and that seems to. But what I always used to say is it's as if I had a class where there were two students named Tim and Tom, and they sat next to each other, and I'd never figure out which one was which. And after I'd used that line in class for years, wouldn't you know, a class came along where I did have two students named Tim and Tom, and they did sit next to each other, and I didn't have any trouble keeping track of which one was which at all. So I guess there's no excuse for you. Anyhow, torque, you know, tension means how much force is in the rope. That's measured in newtons. Torque is Newton meters. You have to multiply the force by how much leverage it gets, which in this case would be the radius that it's unwinding off of. So you do not put the 15 newtons in here. You put 3 Newton meters in there. And my red pen is waiting for you on that one also. Part of the art of teaching is to strike just the right amount of terror into the students. Not enough and they get apathetic. Too much and they get turned off or might even drop the course. You got to walk that line right in between. Keep them kind of frightened, but not seriously so. Unfortunately, that line is in different places for different students. But we put in the 3. For the torque. Put in 0.10 for the inertia. Alpha is what I want to know. And from here, it gets pretty straightforward. You divide both sides by 0.1. But remember, that's not what the question asked for. That's just an intermediate result. Omega final squared equals omega initial squared plus 2 times alpha times delta theta. This is what the question asked for. How fast is the thing spinning around in the end? The initial, we can just get rid of that right now because it started from rest. So take the square root of both sides to solve it for the thing we're looking for. And I have to stick the numbers in there. Okay, alpha, I just got done calculating that that's 30 radians per second per second. Now, here's a spot where some people would get caught also. Theta, the angle it turned, it says 10 revolutions. Well, this is one of those equations where it does not matter if you use revolutions or radians. It works just fine no matter what you measure your angles in. But like any equation, you have to be consistent, okay? If you're calculating something else, you can't have this number in meters and that number in inches. They've got to all match. Same thing here. Since this one's in radians and the theta's in revolutions, you have to convert. It doesn't matter. You could convert radians to revolutions on this number, or you could convert revolutions to radians on that number. It's okay either way, but they have to match. I'm going to go with radians. So I've got the 10 revolutions that was given in the question. And the conversion is that 2 pi radians equals 1 revolution. revolutions going to cancel out. And so now we've got 20 pi radians for theta. Push the buttons. Your calculator tells you that that is equal to 61.4 radians per second. Back over here. Oh, hey, it focused right away. How nice. Next thing on the list is just a sort of a passing mention of rotational kinetic energy, a topic I'm going to cover properly in another week or week and a half or somewhere in that general part of the course. But the thing is, it comes up in the lab that we do, lab number 7. So it isn't that much of a strain just to say, hey, here's this formula, so now you've seen it. The work that an object could do because of its motion is called kinetic energy. Something that's spinning around is capable of doing work, just like something that's moving from place to place is capable of doing work. So there is rotational kinetic energy, just like there was, earlier in the course, we had translational kinetic energy, 1/2 mv squared, like the energy of a bullet as it moves. Here, like the energy of a flywheel as it spins around, 1/2 I times omega squared. This is another one of those equations where you have to have radians. And all of that will be explained in more detail than you probably really want to see, like I said, about a week into the future from this point. So now, one more sample problem, and that will take care of section 7. Right about there. So you've got a rod, which is pivoted at the bottom end, and it starts out vertical, but of course, that's unstable. Somebody on the other side of the room gets the hiccups, and that's enough of a disturbance, it makes it start to move. And as it tilts over, it's going to go faster and faster. So we see it here at 2 different times. This is when it, the instant when it stops being at rest and starts moving. So in the before picture, it's at rest, and this long rod is vertical. And after a short time, we see it, of course, it's in motion, it's swinging downward, but this is like a snapshot, like you took a photograph of it. At this particular instant, you got a 53-degree angle. This 800 grams is 1.2 meters to the left of the pivot point now. And first of all, find the angular acceleration. Now, second, I'm organizing over here. You might be tempted to use this equation. Well, actually, no, we'll get to that when we get to that. First of all, the angular acceleration. This is going to be another torque equals I times alpha type of thing. I'm going to calculate the amount of torque that acts on it in this position. I'm going to get the system's moment of inertia, and I'll solve for alpha, and we'll get that taken care of, and then I'll talk about part B. So 12, part A. Little sketch where I can label a thing or two would be a good idea. We've got some sort of a hinge down here. This rod people see the word rod and they immediately leap at let's see, formula sheet. Thin rod rotating about one end, 1/3 ml squared. Read the question. A lightweight rod. Yeah, the moment of inertia of the rod is 1/3 ml squared, and m is approximately 0, okay? The inertia, the mass is not distributed all along the rod. I guess I should be pointing at this because you can't see the handout there. The mass is all in a little ball on one end. You've got what amounts to a particle. To a good approximation, all 800 grams is located at this point. So it's not a rod. The rod is just a few grams, light enough that we can ignore the weight of the rod. We've got 0.8 of a kilogram, the force of gravity on that. .84 newtons. 7.84 newtons pulling along that line. Now, if you like doing things the hard way, you can figure out the torque like this. You can say, okay, torque is R sine theta times F. So I haven't drawn it all on here, but we've got enough information that you could get the length of this from the Pythagorean theorem. That's R, and you're given the angle, and that'll get you the right answer if you don't make any mistakes along the way. But why go through all of that when the question tells you that from there to there is 1.2 meters. If you go to the trouble of figuring it out, start again, apparently can't talk. If you go to all the trouble of figuring out R and then multiply it by sine of theta, you are going to get 1.2 meters, which you already knew in the first place. So the quickest, easiest way to get the torque here is just to say the force times the moment arm, tau equals F times L. 7.84 newtons times 1.2 meters is 9.41 Newton meters. So we're going to get alpha from tau equals I times alpha. That's tau. For the moment of inertia, just to repeat myself, you're not interested in the formula for a rod because the rod doesn't weigh anything to speak of. The mass is concentrated at this point up here. For a point-like particle, inertia is the mass of that particle times not the radius of the particle, which is effectively 0, but the radius of the circular path it follows. And filling those in, we've got 0.8 of a kilogram for the mass. Now, is that given on there? Yeah, actually, I wasn't looking at the question very closely before when I was talking about the Pythagorean theorem. I guess you're not going quite as far out of your way if you say r sine theta, but you're told the rod is 1.5 meters long. That would be the radius of the circular arc that this mass is moving along. So that's the wrong part of the blackboard. I'm over here. 1.5 meters, and we get 1.8. So I've got tau, I've got I, just like I've said twice before, alpha would be the torque divided by the inertia. Torque equals I times alpha, and then divide both sides by I to solve it for the thing I'm looking for. So 9.41 divided by the 1.8, 5.23. Answer to part A. I'm going to need some space over here for part B. So back to the question for a minute. Less of an angle like that. The angular velocity in the after picture. In other words, omega final. Omega initial equals 0. What is omega final? Well, we know the angle that it turned in between, and I just calculated alpha, so it would seem I've got everything in this equation except for omega final, and I ought to be able to just drop the numbers in there. But if I do, I get the wrong answer. And in parentheses, it says why? Because this equation and the others, you know, its little friends that it has in that group there, those 5 equations assume a constant acceleration, which is not the case here. This equation is invalid because alpha is not a constant number. It changes. The reason you can tell it changes, let's go back to my sketch I made up here. The angular acceleration is proportional to the torque. Well, the torque keeps changing as the moment arm keeps changing. When this thing starts out being right straight up, and that doesn't really show up very well. When this thing starts out being right straight up and down like that, the torque is 0. But some minor disturbance makes it start to fall and gets to about there, and the 7.8 newtons is multiplied by 0.1 of a meter, and it goes a little further, and now the force is multiplied by 0.2 of a meter, and then 0.3 and 0.4, and the farther this thing goes, the longer the moment arm gets. So from one instant to the next, this 1.2 keeps changing, which means the torque keeps changing, which means alpha keeps changing, which means that equation is just going to give you garbage. What will work instead is to use conservation of energy, because that gets around all the complicated stuff that happens in between the two pictures. All it does is compare before and after without making any assumptions about what's going on in between. So that is the way to do it. Okay, so that summarizes what I probably spent 5 minutes saying just now. This equation is only for constant angular acceleration because the torque increases as the lever arm increases. You've got a changing angular acceleration. It makes the thing invalid. So what will work is to say E initial equals E final, because well, I guess the question never comes right out and says you should consider this to be a frictionless situation, but well, you know how it works in these elementary courses. Unless the question says something to the contrary, you can assume friction is small enough to ignore. So to begin with, our 800-gram mass is elevated. It has some potential energy. In the before picture, it's not moving yet, so there is no kinetic energy, but it's it's got MGH. As time, I guess I'm over here. As time passes, it gets lower and lower, losing potential energy, but it picks up speed as it rotates around the hinge. So in the end, well, depending on where you measure your heights from, it's still got some potential energy in the end, just not as much. What you might want to do is, if you measure your heights from where it is in the after picture, you could make this term equal 0. And what you would do over here is you'd call the initial height, I guess it would be 0.6 of a meter. And that's a good way to do it. I thought maybe it sounded more straightforward to just copy the numbers right off the picture without fooling around any, and call the initial height 1.5 and the final height 0.9. And that works also. Actually, it might be a little easier the other way, but I've got it all written out. Well, actually, oh, I see what I did. Yeah, that's good. Let's just rearrange it like this. I subtracted H final from both sides, then factor out the mg, and I'll come over here to fill in the numbers. Mass, 0.8 of a kilogram. Gravity, 9.8. H initial minus H final, 1.5. 0.5 meters minus 0.9 meters. So you have a change in height of 0.6 meters. No matter where you're measuring the height from, it'll change by 0.6. The moment of inertia, I had calculated that, it's still over here. I calculated the moment of inertia when I was doing part A. So we've got 1.8 for that. And now the rest is just math. That times 0.6 is 4.70. Half of 1.8 is 0.9. So the numbers come out 2.29 as for the unit. This is one of those equations where it's built in that you're in radians. And the top of the next page says section 8. So I think it's time for me to end this recording.